Alright, in this video presentation we're going to take a look at the introduction to electrochemistry. This topic applies to both Chemistry 40S and the AP Chemistry 42S as a good introduction. Electrochemistry has two essential aspects. About 80 to 90% of our unit is going to focus on the first aspect, which is taking a redox reaction, we'll get into that later, an electrochemical reaction, one that is spontaneous, meaning from an equilibrium perspective that it has a large Kc value, and that's a very important idea. Okay, a spontaneous reaction means that it has a large Kc value, and we're going to take that electrochemical spontaneous reaction and use it to generate electricity. We're going to use it to produce electricity. So if you have a spontaneous electrochemical reaction, you can use it to create a battery, essentially, and that's what we're going to spend most of our time on in this unit. But there's another aspect, and it's sort of the opposite perspective. You might have a non-spontaneous electrochemical reaction, in other words, one with a small Kc value, so it doesn't really want to make much products. And we can use electricity to force the reaction to produce products. So using electricity to force a non-spontaneous electrochemical reaction to occur is the remaining part of this unit. Most of our attention is going to be on the first item, but we will spend some time on the second, and it's going to be more mathematical. It's going to involve electrolysis, electroplating, things like that. There's two fundamental processes involved in all electrochemical reactions, and those are called oxidation and reduction. If you've taken some biology, you may have encountered those terms already. So let's jump in and define them. There are several ways to define each of the terms, but essentially reduction, as we'll see, is going to be the opposite of oxidation. So here are four ways to define oxidation. Of the four, the first is by far the most important for us, so I put it in bold. Oxidation is the loss of electrons. So in an electrochemical reaction, something is losing electrons, and therefore, as we'll see in a moment, something's gaining electrons. Electrons are being transferred. So in a way, like acid-base reactions transferred hydrogen ions, electrochemical reactions transfer electrons. So the thing that is losing electrons is said to be oxidized, and that's what oxidation is, the loss of electrons. When you lose your electrons, you are going to see your charge increase. So for example, if you look down below at the example reaction, the magnesium on the left starts off with no charge. It's neutral, so you might say its charge is 0. On the right, we see magnesium oxide, an ionic compound, and we know that in the ionic compound, magnesium, being an alkaline earth, has a charge of +2. Now, an oxidation state is not exactly the same as a charge, but it is very similar. So you can see the charge increased from 0 to +2. So that means the magnesium in this reaction was being oxidized. So the loss of electrons results in an increase in your oxidation state. We'll talk more about oxidation states later and see how they're connected to charge. An old way of defining oxidation, in fact the way that this definition is where we get the name oxidation from, is the addition of oxygen. And that's very common in biological examples of oxidation. And that's what's happening in the example down below. The magnesium starts off as just Mg, and then it combines with oxygen. So again, by that definition, magnesium is being oxidized because oxygen is being added. In many biological, biochemical reactions, you also see hydrogen being lost. And so a compound loses hydrogen is also a sign of oxidation. Reduction is just the opposite process from oxidation. Instead of losing electrons, you're now gaining electrons. And because you gain electrons, and remember that electrons are negatively charged, you're going to now see that your oxidation state, your charge, if you like, decreases. And that's where the name reduction comes from. So you are reducing your charge, or if you like, you're reducing the amount of oxygen. As you can see in the third definition, you're losing oxygen. You're also sometimes adding hydrogen. Now it's important to note that in all reduction processes, the first two items must occur. In some reduction reactions, the third, and in some, the fourth will occur. And the same is true for oxidation. All oxidation reactions involve losing electrons and therefore an increase in oxidation state, but only some oxidation reactions will involve oxygen or hydrogen. In the example down below, we again see the ionic compounds, and if you look closely, you'll see the magnesium on the left is again +2, and on the right it's now 0 charge. So +2 down to 0, the Mg2 plus gained electrons. So the Mg and the MgO was being reduced. A little bit of humor. Hopefully you appreciate that. Let's talk some more about those oxidation states. Okay, they're somehow connected to charge. Now, if you are a keener, if you might take some university chemistry at some point, you could write down this little description, but I'm not going to ask you in grade 12 chemistry or even in AP chemistry to define oxidation states. But essentially what we're doing is we're playing a game where we pretend that there's no such thing as a covalent bond. You remember from an earlier unit that covalent bonds often have differences of electronegativity between the atoms, and that leads to polar and nonpolar covalent bonding. With oxidation states, what we assume is that when there's any difference of electronegativity between two atoms in a bond, we will give the electrons to the more electronegative element. So what that does is it makes the more electronegative element suddenly look like it has a negative charge, and the less electronegative element in the bond looks like it has a positive charge. So in other words, what we create when we assign oxidation states are imaginary charges. And this is what you could write down if you want. So oxidation states can be thought of as imaginary charges. And when you play the game of assigning oxidation states, you're able then to track within a chemical reaction which substances are gaining and which substances are losing electrons, as we just did in those reactions with magnesium. There's a set of rules for assigning oxidation states, and these are important to know, so make sure you memorize these rules. And most of them are relatively logical, especially when you remember that an oxidation state is pretty much like a charge. Now, a note, oxidation states are also often called oxidation numbers. Okay, so those mean the same thing. The first rule says if you see an element, pure neutral element, then the atoms in that element will have an oxidation state of 0. And notice it doesn't matter whether there's a subscript or not. A Hofbrinkel element, diatomic elements like fluorine or nitrogen, the oxidation states of every element, of every fluorine atom there, of every oxygen atom in ozone, this potassium atom, I'm going to stop trying to draw with my mouse, but in every one of those elements, the oxidation states are 0 because they're just plain neutral elements. The second rule is also relatively straightforward. If you see a monoatomic ion, so now not just the symbol of an element, but there's a charge beside the symbol to indicate that it's an ion, okay, a charged atom. Monoatomic because it's got one atom in the formula. Now the oxidation state is equal to the charge on that ion. Now there is a tiny little difference. Take a look. Let's look at aluminum. Aluminum, we would say the charge is 3 positive, as I've shown there. But if you're going to write the oxidation state, you should put the sign positive and then the number 3. So plus 3 would be the oxidation state. 3 positive would be the charge. For Fe2 plus, 2 plus is the charge, and plus 2 would be its oxidation state. For the oxide there, -2 is its oxidation state, and for the fluoride at the beginning, -1 is its oxidation state. This next rule is really important, as is the following one, because we use these next two rules to determine oxidation states of other elements. So what we see here is we're talking now about compounds, okay, and technically covalent compounds or complex ions. Within compounds like this, the oxidation state of oxygen atoms is almost always, 99.9% of the time, is going to be -2. Okay? In fact, 99.999% of the time, it's -2. So in this example here, in brackets, is the formula for methanol, and I see there's an oxygen in that formula. That oxygen's oxidation state would be -2. Now, if you wonder what the exception is, because it says almost always, if you're a real keener, there's a complex ion called the peroxide ion. This is one common exception, relatively common, O2, 2-. A very common example would be hydrogen peroxide, which has the formula H2O2. In this complex ion called peroxide, there's two O's, and the entire thing has a charge of 2-. So each of the O's has a charge of 1-, or an oxidation state of -1. So in the peroxide compounds, the oxygens there are -1, not -2. Now, if you don't ever remember that exception in grade 12 chemistry, you're probably perfectly fine, okay? Hydrogen, when it shows up in a compound, and there's hydrogen in methanol, just like oxygen, it's almost always, 99.999% of the time, going to have an oxidation state of +1. Okay, so hydrogen in a compound is +1. The exception for hydrogen is when you see it bonded to a metal. When hydrogen's bonded to a metal, for example, calcium, Ca, H2, it's really hard to write with a mouse, CaH2, now you can tell something's funny happening with hydrogen, because we know that calcium, a metal, has a positive charge. In fact, this must be an ionic compound. So the calcium here is +2. So these hydrogens bonded to it must now be -1. Okay, so if you really pay attention, you'll notice that I said this was an ionic compound, but earlier we were talking about oxygen and hydrogen when they were in covalent compounds or complex ions. Okay, but in an ionic compound like CaH2, we see hydrogen here is called hydride. Okay, so this is calcium hydride, and so there the hydrogen is not +1, it's -1. The last two rules, if you see oxygen, if you have a compound, the sum of the oxidation numbers, the oxidation states in the compound, has to equal 0 if the compound has no charge, if the compound is neutral. If the compound does have a charge, so now we're talking about a complex ion, then the sum of the oxidation states must equal the charge on that ion. All right, so pause the video and make sure you've got all of those rules written down, and then we'll take a look at some examples on the next slide. So in this exercise, I want you to write the elements, the symbols down, the formulas down, and above each element, write down its oxidation state. Pause the video if you like and copy them down, and then we'll start looking at them one by one. So the first one, H2, hopefully you recognize that would be just an element, hydrogen. It has no charge beside it, it's a pure element. So by the first rule that we saw, its oxidation state is 0. So we'd write a 0 above it saying each of the hydrogen atoms there is 0. In the example beside it, SO3, we had a rule that said oxygen in a compound is -2. We had another rule that said the sum of the oxidation numbers, the oxidation states, must equal the charge on the compound. And Here, there's no charge. There's no symbol beside it to say a charge. So here, they have to add up to 0. So, excuse me, if you have 3 oxygens, and each of the oxygens is -2, then that one sulfur has to have an oxidation state of +6. A simple way to test this is there's 1 sulfur in the formula, so 1 times 6 is +6. 3 times -2 is -6. And 6 and -6 cancel out and give you 0, which was the charge on the compound. So I know I've done that right. Next we have the sulfate ion. Again, we know those oxygens are each -2. So I'm going to put a -2 above the oxygens. There's 4 of them. 4 times -2 is -8 total. So that sulfur must be, now wait a minute, there's a charge on this thing. The charge is -2. That's different. So if you've got -8 from the oxygens and the entire thing has to end up being -2, that sulfur must have an oxidation state of +6. And let's just verify that. 4 oxygens, 4 times -2 is -8. 1 sulfur, 1 times 6 is 6, and -8 and 6 add up to give that charge -2. So that's definitely right. The next example, we have K+, a monoatomic ion. It has a charge, so its oxidation state is the charge, in this case +1. Ammonia, NH3, the H's this time we could start with. We know that when H is in a compound, it's almost always +1. So there's 3 of them bonded to 1 nitrogen. That nitrogen must be -3 because the entire compound is neutral. Permanganate. There's oxygens, so they're -2, 4 of them, and 1 manganese. Now remember here, again, it's an ion, so the total charge has to equal -1. So now the manganese must be +7. Just to verify that, 4 times -2 is -8. -8 and 7 is -1, the charge that's on the ion. Next we have dichromate, which is probably the hardest example on this slide. You've got oxygens, which are again -2. There's 7 of them. 7 times -2 is -14. The entire thing has a charge of -2. So if you've got 14 negatives, you'd have to have 12 positives. 14 negatives and 12 positives would give you the -2 charge. Those 12 positives, though, are divided this time over 2 chromiums. There's 2 CRs in the formula, so each of the chromiums would be +6. And double check, 2 times 6 is 12, 7 times -2 is -14, 12 and -14 give me the -2 charge. Methanol, the H's are +1, the O is -2, so the carbon there must be -2. There's 4 H's, 4 times 1 is 4. There's 1 carbon, 1 oxygen, -2 is -4, and the entire thing was neutral. That makes sense. Phosphate, the O's are -2. There's 4 of them. 4 times -2 would be -8. The entire thing has a charge of 3-, so the phosphorus there is +5. Chlorate, the O's are -2. There's 3 of them. 3 times -2 is -6. There's 1 chlorine, and the entire thing has a charge of -1. So if you have -6 from the oxygens, you'd have to have +5 from that chlorine. 3 times -2 is -6. -6 and 5 gives me the -1 charge. HSO3-, the O's are -2. The H is +1. 3 O's would be -6. -6 and +1 would be -5. The sulfur here must be +4 to get a charge of -1 as the overall charge. And finally, copper is just the element copper. There's no charge beside it, So it's a oxidation state, like hydrogen at the beginning, would be 0. What if you were looking at an ionic compound? An ionic compound like silver nitrate, if you try to follow the rules as we did it just on the previous slide, you'd probably run into a problem. You'd run into a brick wall. The problem is that silver nitrate has two elements, silver and nitrogen, for which we would not have any rule to assign an oxidation state. We would know that oxygens are -2, we would know that the entire thing is neutral, but how would we decide what the silver and the nitrogen's oxidation states should be? We'd have a problem. The key is to recognize that silver nitrate, because it starts with a metal element, silver, is an ionic compound. And ionic compounds are by definition made up of ions. So begin by separating the silver nitrate into its two ions. In this case, silver cation, whose charge is +1. You know that from your grade 11 chemistry. In our data booklets, page 6 of the data booklet shows the charges on the ions if you're rusty on that. The nitrate ion, NO3, has a charge of -1. Now consider each ion separately. Silver, Ag positive, is a monoatomic ion, so +1 would be its oxidation state. The O's in nitrate are -2, so the nitrogen must be +5. The entire thing was -1 for nitrate. Try another example of that. Calcium bromite, CaBrO2, 2. Okay, again, do you recognize that it's an ionic compound? It starts with a metal. Then break it apart into its two ions. Calcium bromite would be composed of calcium ions, Ca2+, and bromite ions, BrO2-. Now consider each of the two ions separately. The calcium here would have an oxidation state of +2. The oxygens in bromite would be -2. And because the bromite's charge is -1, that bromine atom would be +3 as an oxidation state. So those are the rules for assigning oxidation states, the definitions of oxidation and reduction, a good introduction to electrochemistry.